Good evening. Welcome to lesson 5.2. This is on polynomial long division. In this video, we're going to talk about two sort of types of division. The goal is we're going to be dividing polynomials. So, a polynomial, something like this, right? And we're going to divide that by something like another polynomial, something like that, right? And so that's the premise. So we're going to explore two things, was long division as well as something called synthetic division. And that's the topic of this video. So let's just get started here with some definitions. And now you notice it says review of lesson 5.1. So this information here comes from the last lesson, but it's a good thing to remind ourselves, review. These definitions are important. I wouldn't put this on the notes twice if it wasn't, right? Excuse me. So the first thing is, what does it mean to be a factor, right? Don't forget it, right? I mean, I know we say this word all the time, but you say it over and over and you do a bunch of math, but do you remember what it means, right? If n is an integer, then a is a factor of n if a divides n. That's what that says. It says a divides n. Doesn't mean a divided by n. That's not what that means. It means a goes into n. It divides evenly into that number, right? And as a quick review, right, we say that 6 divides 12 because 6 goes evenly into 12. 8 does not go into 12, right? So we would say that 8 does not divide into that. 6 is a factor of 12, 8 is not. Okay. And so we know what factors are for integers. It's similar for polynomials, right? It's pretty much the same definition. If you let p and q be two polynomials, then q is said to be a factor of p if q goes into p, right? That is, you can do p of x divided by q of x, and it generates some other polynomial, right? It gets another. That's what would constitute it being a factor. So I would put a bunch of little stars right here. I would just say, ooh, this is important. Look at all those little stars. These three things, you want to know these, yeah? You want to know that if q of x is a factor of p of x, which of these are, these three things are true, and you need to know it. I mean, you got to burn it in your brain, right? So the first thing is, the quotient of p of x over q of x, that is, like what I just wrote, when you divide those two polynomials, where q is a factor of p, that creates another polynomial. We discussed that in the last video, right? The other thing we talked about was the degree. So the degree of your divisor, so we say the degree of q of x is supposed to be less than or equal to the degree of p of x, okay? This is kind of that idea, and I mean, I covered this in the last video, but it's just a quick review. You know how if I say 6 goes into 12, 3 goes into 12, right? Does 24 go into 12? Well, no, it doesn't, because 24 is bigger than 12, and any number bigger than 12 won't work. You might ask yourself, well, does 12 go into 12? Yes, it does. 12 does divide 12, so we can say that 12 is a factor of itself, right? So this logic sort of carries on over to factors with polynomials. If you have, x to the sixth, blah, 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 maybe x cubed divides x to the sixth, blah, 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 right? And that could happen. Or you could even have x to the sixth divide itself. But you would never have a higher degree like x to the eighth divide into another. That's not going to happen, right? So, if it's a factor, the degree of that factor is less or equal to, right? And lastly, the roots of q of x, so that divisor polynomial, are also roots of p of x. And I would say that's the most important one. Yeah, that's very important. That's why factoring works. Okay, or that's why factoring finds solutions. Okay, a quick review on long division. Traveling back to the third grade here, if n is an integer and a divides evenly into n, then the quotient n divided by a is an integer with no remainder. Just think about that sentence for a second. I mean, if you need, just pause the video and read that again, right? What does it mean to divide evenly into something? It means that it goes in there when you do the division of it, right? The quotient of that division gets you a whole number with nothing left over, right? So here's just a few practice problems. I'm going to change this to black, just kind of, give me that straight. Oh, look at that. I'm going to make this, straight, boom. Okay, I'm going to zoom in here. So, yes. Now look, if you know what long division is, you can skip this, okay? It's fine. But just in case you've forgotten, and it's always helpful to have a review, the way long division works is you take this number and you look at the highest place value, right? The place value to the furthest left, and you ask yourself, how many times does your divisor go into your dividend, right? I'd say, look, 3 goes into 3 one time. And so I do 3 times 1 is 3, and then I subtract. I do 3 minus 3, hey, that's gone. And so I drop the 2. And I ask myself, well, does 3 go into 2? No, it doesn't. So it goes into 2 0 times, and then I sort of drop the place value, so it becomes 20. And now once it's 20, I say, okay, well, 3 times 6 is 18, and 20 minus 18 is 2, and then I'm going to drop the 1, because that's how long division works, right? And 3 goes into 21 7 times. And you'll notice that I get nothing left over, right? The remainder here is 0. I have nothing left over. And notice we're not doing decimals, right? We're not trying to do that. We're just saying, hey, there's nothing left over. 3 divides evenly in there. So yes, it does. And then another example over here. Does 4 divide evenly, right? Well, 4 does not go into 1, but 4 goes into 10 2 times. Subtract, that's 24. 4 goes into 24 6 times. And I drop the 2, and so I say, oh, well, 4 does not go into 2, so that's 0 many times. And that means we have 2 left over. So that means there is 2 remaining, remainder 2. And so because you have a remainder, you would say no. 4 does not divide evenly into 1042. Or in other words, 4 is not a factor of 1042. And I know that seems really simple and probably basic, and well, I'm hoping it does because it's third grade math, right? I hope so, right? You're in advanced algebra too, I would hope so, right? Anyway, I know it seems pretty basic, but if you understand that, then you can understand polynomial long division because it's the exact same thing. You just have to kind of do it with variables and be careful of double negatives, and you'll be fine. And the idea is, if I understand, look, if it has remainder 0, it went in evenly. There was nothing left over, so it's a factor. If it had a remainder that's not 0, then it wasn't a factor. And that's just the underlying idea behind this lesson. So let's look down here at polynomial long division. So if I kind of tweak that definition from before, for polynomials, I say P and Q are polynomials, and Q goes into P, that means Q divides P, then the quotient of P divided by Q is a polynomial with no remainder. So the same way, right? The same way an integer won't have a remainder, polynomials won't have a remainder if it divides evenly. Next is a corollary. And so what a corollary is it's just kind of a logical conclusion of another like a logical statement. So because I've said this thing before, logically the next statement follows. Yeah, and you don't have to prove it or anything like that. A corollary just kind of directly comes from another thing. There's your math vocabulary for the day. And so it says if a quotient P of x divides Q of x has a non-zero remainder, that basically means it's not 0. You had something like 2, right? Then that means Q is not a factor of P, right? So the idea is if it's a factor, it has no remainder. If it has a remainder, it is not a factor, right? It means basically the same thing. Okay, let's do example 1 here. And so we're going to start with long division. and you set it up basically the same way you set it up like you did in third grade. It's just now your dividend is a polynomial rather than an integer. Let's establish that. Look at that, and I got x minus 6. Now, the way this works, what you're going to be doing is the same way you look at the leading place value, you're going to be looking at the leading coefficient. Now, yes, we have a binomial as a divisor, but what you're really looking at is the leading term. You're just concerned about x, okay? You're using x to make the numbers up here. Kind of ignore that. You don't need the 6, all right? Now, you're going to use the 6, but you don't need to. The 6 does not determine the quotient stuff up here, okay? So you look at the lead term here and look at the lead term that's in your dividend. So I asked myself, the same way I would do with regular long division, x times what is x cubed? I would say, well, x squared, naturally, right? And so I say x times x squared is x cubed, and I put that right beneath. But the thing is you're not just multiplying x, you're multiplying this binomial. So you're doing x minus 6 times x squared, so the x squared distributes to the negative 6 as well, getting you negative 6x squared. From here, I'll draw parentheses and subtract. And the reason I use parentheses is up here, right, the idea is you subtract that thing. You're subtracting that whole entire number. But now that we've moved to expressions, you know, this is a single quantity that you are subtracting, so that negative sign has to apply to both terms, okay? So you do x cubed minus x cubed, gone, hooray. And then next you'll do negative 4x squared minus negative 6x squared. But of course that's just plus 6x squared, so negative 4x squared plus 6x squared, you're going to get 2. You're going to get positive 2x squared. And then I'm going to drop the negative 17, kind of the same way I drop my place values, right? And repeat. And say, okay, look at x, and now look at the leading term. What would you multiply x by to get 2x squared? Hopefully you say 2x, right? X times 2x is 2x squared. Okay, that makes sense. So I put 2x squared here, and then I do, again, right, 2x times negative 6, I get negative 12x. Put my parentheses, draw a minus, carry out the subtraction, 2x squared minus itself, gone. Those are always going to cancel, by the way. Negative 17x minus negative 12x, well, that's like negative 17 plus 12, which is going to be negative 5x. And I'll have to say plus 30 here, again, because I'm just dropping the 30, right? And then finally, to finish it off, you ask yourself, x times what is negative 5x? Well, negative 5, right? Naturally, right? And so again, I'm doing negative 5 times x and negative 6. So I get negative 5x, and negative 5 times negative 6 is positive 30. And I'm subtracting this expression. I don't like that minus sign, it's too long. There we go, that's better. Negative 5 minus itself, gone. 30 minus itself, gone. I'm left with 0. There is nothing remaining. I put remainder 0, right? Say remainder 0. So what does this mean, right? This polynomial, this guy, was divided by another polynomial, and we have another polynomial with a 0 remainder. Conclusion, x minus 6 is a factor, right? It's a factor of that polynomial you divided. And in fact, the factorization, right, is, and I'm not going to keep this for the notes, but the factorization would be this whole thing equals x minus 6, because that goes into it, and the quotient of that was x squared plus 2x minus 5, right? So this times this is this. It's the same way like up here, right? If 3, 2001, right? It is 3 times the quotient, right? I mean, that's how that works. So you found the factorization. There it goes. Now I'll do number 2. Oh, should I switch to blue? But the whole page is in red. Let's just be consistent. So we're going to try number 2 now. it's really no different. It's just more examples. So it says 6x squared minus 10x, sorry, 6x cubed minus 10x squared minus 25x minus 24. Divide this. Get a nice, can I make that? No, that's not it. That's better. And then this is 3x minus 8. No, 3x minus 8. Okay, so same premise. I mean, I hope I don't need to explain it every time. At this point, I'm just gonna kind of walk through the problems because I'm hoping that first example was enough to model it. So again, the idea is you're trying to match the first one with the lead coefficient here. So I say, okay, 3x times what is 6x cubed? Well, 3 times 2 is 6, and x times x squared is 6x cubed. Now I'm going to multiply 2x squared times both terms, and I'll get 6x cubed. Then I'm doing negative 8 times this, gets me negative 16x squared. Subtract, this is gone. Negative 10 minus negative 16 is 6x squared. This is minus 25x. Do it again. 3 times 2 is 6, and then I need another x here. So plus 2x, I get 6x squared. Negative 8 times negative 2 is negative 16x. Subtract. So that's gone. Negative 25 minus negative 16, that's negative 9x plus 24. Yeah. And then I say, okay, 3x, negative 9x, what needs to multiply? You already have an x, so you just need 3 times something to get negative 9. That's, excuse me, that's negative 3. And so I do negative 3 times that, and I get this. And negative 3 times negative 8 is positive 24. And oh my gosh, look at that. Those both cancel. I have 0. The remainder is 0. So conclusion, 3x minus 8 is a factor. Hooray! Yippee! It is a... I'm sorry, I just didn't like the way I spelled that. And look, and if you like, a little happy face. Hooray! Is that how you spell hooray? I actually don't know. I hope so. Hooray! Okay, let's move on. Let's do a few more examples, and maybe a couple of these you want to be a little bit more careful with. So we're going to look at number 3. And this, at this point, this is just classroom practice. This is where I hand it off to you guys and you practice. But because it's a video, you know, I'm gonna go through all of them. If you think you've got it, if you think you've got long division, skip ahead. You don't need to keep watching. It's fine. Go on down. I'll meet you there soon. Yeah, and I'll see you at synthetic division. Okay. So to walk through this problem, x cubed. Now, it says minus 27x, right? So I'm going to show you something. I'm going to set it up like this. And I'm going to do all this. Now you see x times x squared is x cubed. And 3 times x squared is plus 3x squared. Now hold on. Let me subtract this. I know, it's sloppy because I'm going to erase it. This will cancel. But ask yourself, is negative 27x and 3x squared, are those like terms? Can you take away 3x squared from that next term, negative 27x? No, they're not like terms because the powers are different. So I'm going to erase this because I'm going to rewrite it. And you don't have to do it this way. If you can keep track of it, you're fine. But I'm gonna write it a specific way. I don't see x squared as a term, even though that would be the next exponent less than 3. That means the coefficient is 0. And I'm going to just put that there. That way I sort of have that place value. I have that term in place. Also, how hard is it to make a straight line? Thank you. Goodreads. And then this is x plus 3. And so now I repeat the same process. X times x squared is x cubed, and 3 times x squared is 3x squared. You see how that nicely lines up now? Now you're not really, you're not tempted to take away 3x squared from negative 27x, right? Because you've stacked the like terms on top of each other, and that's nice. It's visually appealing. So 0 minus 3x squared, and then minus 27x. And then from there, say, okay, x times what? That's negative 3x squared. You find that's negative 3x. You should get negative 3x squared here. 3 times negative 3 is negative 9x. Subtract. These are gone. And negative 27 minus negative 9, that's like plus 9, is negative 18x. And this is minus 54. And so you say x times negative 18 gets you negative 18x. And 3 times negative 18 gets you negative 54, believe it or not. And you subtract these, and you get 0. So you'll notice these are 3 examples back to back to back where all of the remainder is 0. Is it going to be 0 every time? And no, it's not. But these first 3 examples were. So x plus 3 is a factor. Move on to number 4. Now, it's really not different, but I will just call your attention to the previous things you've been dividing were linear terms, right? The divisors were x plus 3. Excuse me, my goodness. Hopefully somebody's saying bless you. Say bless you, Mr. Spake. This is also linear. This is also linear. But this is not. That's quadratic. So notice I'm dividing a degree 4 polynomial by a quadratic. It's going to be interesting. We're going to see what happens here. And when this happens, pay very close attention to which ones are like terms. I do recommend stacking like terms. Oh, that's bothering me. You see how that's just barely slanted? Oh, that's getting me. Say, no. Straight. That's better. Okay. Same process. X squared times x squared is x to the 4th. So that's x to the 4th. But 4 times x squared, that's not a cubic term, right? That's quadratic. That's plus 4x squared. Notice how I aligned that underneath the like term. That way I don't get confused, because if I put plus 4x squared here, my brain might be tempted to take away this from this, right? It's not to say that you can't, it's just that you might be tempted to. And so this one's just going to drop. It's fine. Like that's now the lead, right? And it just drops. Because essentially there's 0x cubed beneath that. Now 3 minus 4 is negative x squared. And then I repeat. So I say x squared times negative x gets me negative x cubed. And so I say, okay, then that's negative 4x. Ooh, I should probably drop that negative 4x so I can take it away. So I'm going to drop the negative 4x here. That way, when I do 4 times negative x, I could put that beneath it. And you'll notice that those are actually the same exact term. So both of our stuff everything's going to cancel here. Those are going to cancel. And negative 4 minus negative 4 is also going to cancel, right? They're going to both sum to 0. And I get negative x squared minus 1. Finish this off. X squared times negative 1 is negative x squared. 4 times negative 1 is negative 4. Subtract this. These are now gone, but negative 1 minus negative 4, that's like negative 1 plus 4 is 3. So, finally, at last, an example where the remainder was not 0. So it's called remainder 3. And so conclusion, x squared plus 4 is not a factor. But also, what is the quotient, right? And I guess I did not, look, I should probably write, let's do it in gold. The result, right, the quotient which was your result, was x squared minus 3x minus 18, right? And on these other two, your quotient, so you can skip ahead of this if you don't care. It's fine. Just skip ahead like 10 seconds, 15 seconds, right? I'm just getting these in here. The quotient is the thing on top, right? 2x squared plus 2x minus 3. See how everything I've written in yellow, they're all polynomials, right? But here, what's your quotient? It's x squared minus x minus 1, but there's 3 remaining. The question is, what are you going to do with that 3, right? You can't just write remainder 3. I mean, I guess you could, but that's not how we do things, right? I think if you went back to this example, you see how this is 260 remainder 2? If you go back to 3rd grade and you did this with fractions, this is like saying 260 and 2/4, right? Because think about, you have 2 left over that is still yet to be divided by 4. So that remainder 2 is getting divided by 4, means it's 2/4, and of course we simplify that as 1/2, right? So use that exact same logic on this problem. The remainder is 3, so you're going to, let's get rid of the purple. You're going to say, oh, I have 3 left over, but it's trying but it's trying to be divided by x squared plus 4. Because it does not divide evenly with that, right? And so that is my quotient. Okay? So again, when you have a non-zero remainder, just add it or subtract it if it's negative, right? Add it to the polynomial, but keep it as a fraction over this. And by the way, this is not a polynomial because of this term, okay? All right. If you skipped ahead, welcome back. This is synthetic division, also known as Ruffini's rule. I hope I'm saying his name right, Paolo Ruffini. So what Ruffini's rule is, and by the way, today this is just really called synthetic division, but he's the guy who kind of came up with the algorithm. And it's a sort of algorithmic shortcut that's an alternative to long division. So instead of all this work up here, which is not so bad. I mean, it's a lot of writing, but it's not too bad, right? Ruffini's rule is a way of streamlining this process. But today, as we talk about synthetic division, it's only going to work with monic linear factors. Now, you know what linear means. You know what factor means. Monic is a new word, but all monic means is a polynomial with a leading coefficient of 1. So example, x plus 7 is a monic linear term, right? X minus 3 is monic linear. X squared plus 1 is monic, but not linear. It's not linear because of that exponent. 3x plus 1 is linear, but not monic because the leading coefficient is 3. Okay? So that's to kind of do that. Now, before I begin with synthetic division, this method I'm about to show you, there's an alteration you can do to it to work with non-monic polynomial divisors, meaning it'll also work with like 3x minus 1, and it could work with x squared plus 2, or even 4x squared minus 3. So there is a version of synthetic division that works with this, but it's an extra credit assignment that you can check out soon. If you're watching this in 2023, I probably haven't posted it yet, but if you're watching it later, I probably have. I don't know. So anyway, just keep in mind, as far as our class goes, don't use this unless it's a monic linear factor, okay? Okay, here's how it works. So the first thing you do, set up the coefficients of the polynomial you're dividing. So in this case, it's x cubed is my first term, right? So the coefficients are 1, negative 4 on x squared, negative 17 on x, and 30 as the constant. So you set up the coefficients of the dividend polynomial. Now, look at your divisor. What are you dividing by? I'm dividing by x plus 6, or sorry, x minus 6, right? What you're going to use is the root of the divisor. So you use the root of the divisor. So ask yourself, okay, what's the root of x minus 6? X minus 6 equals 0, because that's what a root is, right? It makes a function 0. So x equals 6 is our root. So what I'm going to do is I'm going to create this nice little box here. I'm going to put 6 in there. And that's my special root, okay? And essentially what I'm doing here is I'm sort of testing whether the root is a root. Yeah, it's kind of like, it's sort of like plugging the root into the function to see if it is in fact a root. And so here's how synthetic division works. I'm going to draw a line here, and that's going to straighten out. There we go. With the first coefficient, just drop it down. So it's 1, drop it down. There's 1. And now the process is multiply, add, multiply, add, multiply, add. Okay, so you're just going to repeat that process over and over and over. You say, what do you mean by multiply, add? You're going to take the number that's in the bottom in this line down here. You're going to multiply it with the number in the box, which, as a reminder, is the root of the divisor. You're going to place that result on the next term, and then you're going to add those results. Once you have that, you're going to take this result down here. You're going to multiply it by the root of the divisor. You're going to add that result down here and add. Okay? So this is what this looks like. 1 times 6 is 6. Negative 4 plus 6 is 2. 2 times 6 is 12. And negative 17 plus 12 is negative 5. Negative 5 times 6 is negative 30. 30 minus 30 is 0. And you're done. The synthetic division has worked. Hooray! You'll notice, let's see, 1 times 6 is 6. This added is 2. 2 times 6 is 12. This added is negative 5. Negative 5 times 6 is negative 30. I just want to be sure that that's clear to you in the video, okay? Now from there, what do we make? Well, okay, great. What do you make of this? Well, I'm going to call your attention. Look at that nice, pretty set of numbers. Just really look at it. 1, 2, negative 5, 0. Just, oh, look at that. What pretty numbers. I'm going to go back, and I also want you to notice, you see this problem here? We already did this problem. We did it right here. And what was your quotient? Oh my gosh, it was 1, 2, negative 5. Hey, look at that. Synthetic division yields the coefficients of the quotient polynomial. Oh my gosh. Yes. So the way you interpret this result, this last column, the result in this last column, always, always, always represents the remainder. So this is what's left over. In this case, 0 is the remainder. The next term is the constant term. And constant is x to the 0, which equals 1. Okay, as a reminder, pretty much any number to the power of 0 gets 1. Although 0 to the power of 0 is debatable. That's for another time, though. That's totally not this lesson. So that's a constant term, meaning there's no x next to it. Then it's a linear term, then the quadratic term. And it just keeps increasing power as you go to the left. Okay? So the resulting polynomial is 1x squared plus 2x minus 5 with nothing left over. And that's it. You're done. Oh my gosh. How fun is that, right? That is a good time. So that's it. That's synthetic division. And that's how it works. And I'm just going to do the other 3 problems for fun, okay? So let's do number 2 now. It says x cubed plus x divided by x plus 1. So to review this, you need the coefficients of the dividend polynomial. Now, notice there's only two things here. In some students, I ask you to do this in class. I ask you to try it. And here's what about half the class usually says. 1, 1. And then they put a -1 here. And then they do the process, and then they get that. And that's not right. So I ask you, pause the video, and I want you to think about why. Okay, so assuming you paused the video and didn't just keep playing, the coefficients must go on every term in your polynomial. You see, this is 1x cubed plus 0x squared plus 1x plus 0 as a constant. Yeah? So your coefficients are 1, 0, 1, 0. The root of x plus 1 is x equals -1. So I put -1 in the box here. And now I do synthetic division. So I take the 1, drop the 1, multiply, add, multiply, add. 1 times -1 is -1. 0 plus -1 is -1. -1 times -1 is +1. 1 plus 1 is 2. 2 times -1 is -2. And 0 minus 2 is -2. Aha. So now how do we make sense of this, right? This is the remainder. This is the constant. This is the linear x to the 1. And that's the quadratic term, x squared. So the resulting polynomial, or I should have changed this to quotient. That would be better vocabulary. X squared minus x plus 2. But the thing is, you see you have -2 remaining, right? Well, ask yourself, what were you trying to divide by? X plus 1. So that 2 that's left over, that -2, is put over x plus 1 because it has yet to be divided. Yeah? And so it's probably better to call this, let's call this the resulting quotient. Because it's not a polynomial, right? This isn't a polynomial. This was, so that's fine. But that was just our quotient, was just some expression. Okay. That's pretty much it. I mean, I'm going to keep going, and this video is going to be long, because is there more? Oh, okay, there's a lot more to this video. If you get this, move on, okay? Don't wait for me. I'm just doing all the examples for you, okay? All of them for you. So let's look at number 3 here. Here's 2, 16, 32, -5, -20. Notice they were all decreasing powers, 4, 3, 2, 1, 0, okay? So we didn't miss anything. The root of x plus 4, right, is -4. So I put -4 in this box. And now I'm just going to do it, synthetic division. Drop the 2. 2 times -4 is -8. 16 plus 8 is 8. 8 times -4 is -32. Those added together is 0. 0 times -4 is 0. -5 plus 0 is -5. -5 times -4 is +20. And those added together is 0. Again, that's the remainder. That's x to the 0. That's x to the 1. That's x to the 2. That's x to the 3. And so the resulting polynomial is 2x cubed plus 8x squared, no linear term, minus 5. And there's no remainder. So we're good. And that's it. Last one. X cubed minus 12x minus 6. Okay? That's, 1x cubed, 0x squared, -12x, -16. The root is -2. So I drop the 1. Look at a straight line. 1 times -2 is -2. 0 plus -2 is -2. -2 times -2 is 4. That's -8. I don't like that 8. By the way, this is just an aside. I used to, growing up, I always drew my 8s like this. Always, always, always. This is how Mr. Spig drew 8s his whole life. But then I changed to this. I know. And some of you might say, Mr. Spig, that's the little kid way. What are you doing? Little too straight. But I mean, doesn't that look like an 8 better than that? Oh, I mean, I don't know. Oh, that's a pretty nice 8. But then sometimes if you do it fast, it looks like that. It's like, what the heck is that? Is that a dollar sign, right? Anyway, okay, I'm just going on and on. Shut up, Mr. Bake. Get on back with the lesson. Negative 8 times negative 2 is positive 16. Add this together, and we've got our polynomial. Remainder, x to the 0, x to the 1, x squared. So I get 1x squared minus 2x minus 8. Oh, did you notice what I just did? I went back to my old habits. Okay, all that just to not do it right. Okay, whatever. There it is. Hey, what happened here? Hello? Where'd you go? Where'd my answer go? This was 5. I don't know where that went. Okay, moving on. Now, the rest of this was honestly just classwork and practice. You're probably fine to stop the video here, but I don't know. It might be good to continue, okay? Especially if you're stuck on the homework questions. So we're going to use long division to factor, and then we're going to talk about finding roots using factoring. And by the way, this will come up again. Basically, this whole page is just a brief glimpse at what lesson 5.4 goes over. So you could skip this and then just go to 5.4, okay? But up to you. All right. Using long division to factor. So we're going to use factor by grouping, and we're just going to fully factorize this polynomial. So this was just a class exploration, right? So you group the first two terms like this, and then you group the last two terms, excuse me, and then take out the GCF. The GCF here is x squared, and I get x plus 3. The GCF of the other group, well, I don't want my lead to be negative, so I factor out a negative, and I get x plus 3. And now I notice, oh, x plus 3 is the common factor, so it's x plus 3 times x squared minus 1. And x squared minus 1 is a difference of squares identity, so that factors as x plus 3 times x plus 1, x minus 1. Okay? And that's it. You said, that's not new, Mr. Spake. I know, but it was just something to review during class, okay? Now, let's spin this problem around. Suppose, right? So, look, we know this is factorable, okay? Look, we could solve the problem and find all the roots by factoring. We're fine. But we're just trying it a different way, using what we've learned, okay? We see, based off this factorization through grouping, that x plus 1 is one of the factors. So suppose somehow, whether the professor told you or whether you graphed it somehow you knew x plus 1 was a factor, but you didn't know the other two, right? What we're going to do is use synthetic division or long division on this to see what the resulting polynomial is, and then from there you can factor. So this is just to sort of model the process. Now, notice the factor x plus 1 is monic, meaning 1, and linear. So I'm going to use synthetic division because that's faster. Here's my negative 1, and I'm going to do 1, 3, negative 1, negative 3. And so we'll just go through this process, drop the 1, 1 times negative 1 is negative 1. This is 2, and then negative 2, and then negative 3, and then 3, and then 0. Yeah? And so what is the resulting polynomial? Well, it's x squared plus 2x minus 3. But notice, that's just a pretty typical quadratic trinomial that is very easily factorable. So if you look at x squared plus 2x minus 3, you could do your little x puzzle, right? Put the negative 3 up here, put the 2 down here. What two numbers multiply to get negative 3 and add to get 2? 3 and 1. Had to think about that for a second. 3 minus 1 is negative 2, right? And, there's a lot of different, you could do grouping and blah, 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 but we know we can shortcut this and say It factors as x plus 3, x minus 1. So basically what you've done is you divided this by a known factor, got a new polynomial that was easily factorable, right? So we factored that pretty easy, and now you know the full factorization, right? The complete factorization is what, right? Well, it's the quotient you found, x plus 3 times x minus 1, but don't forget, x plus 1 was a factor we knew, so that's still part of the factorization. And, of course, that matches the result we just obtained in the above part. Now, and this is the point of the activity here, the structure. It says not all polynomials can be factored using the methods you've learned. So try grouping on the next one, right? That's the idea, is you'd get stuck here. So when you have x cubed minus x squared minus 16x minus 20, right? Like this. So I'll factor out x squared, so I get x minus 1, and then I'll factor out negative 4, and I'll get 4x plus 5, right? And that's just through grouping. Group this, group that. That is hideous. Oh my gosh, I can't bear to look at that. That is just gross. Now that is beautiful. Okay, much better. And so there it is, right? Uh-oh. I say uh-oh. Right? I can't factor from here. And the reason is this term and this term are not the same, right? Up here, x plus 3 and x plus 3, because that was the same term, right, the same binomial, that counts as a common factor, and then you're left behind with that and that. But this and this aren't the same thing. They're not common factors. So, how do you factor that, right? Well, suppose somehow, and I don't know how we know this, but somehow we know that x minus 5 is a factor of this. So grouping didn't work, but you know one of the factors somehow. This is a monic linear factor, so we'll use synthetic division because we like it. And the root of that is 5, right? So synthetic division, drop the 1 times 5, that is 4, then it's 20, then it's 4, then it's 20. Hey, look at that, right? And so the resulting polynomial is x squared plus 4x plus 4. And I don't know if you know how special that is, but that is a perfect square trinomial. I don't know if you knew that. Which means this very easily factors, right? This will factor as x plus 2 squared. And that's if you know your perfect square trinomial factoring patterns. If you don't, it's okay. Just do the x puzzle, 4 and 4. What works? 2 and 2. So you know that it factors as x plus 2, x plus 2, which I just simplify. I just write x plus 2 squared, right? So completely factor the polynomial, right? The complete factorization is, well, it's x plus 2 squared times the other thing, the thing you divided by, x minus 5, right? So it's x minus 5, which we knew was a factor, times x plus 2 squared. And ta-da! You fully factored it, right? Now, you might be saying, now, Mr. Spake, aren't we cheating a little bit? How do you know that x minus 5 was a factor? Tune in to lesson 5.4 to figure out how we may have known 5 was a root. But that's in lesson 5.4, okay? All right. let's wrap up this video. I'm scared to see the timestamp on this. This is incredibly long, but I hope it's helpful. I hope you get something out of these. As long as this is helping you, then it's worth the time, okay? So this last little group investigation is just on finding roots. It's very similar to what we just did, but it's just a longer problem is all. So it says find all roots of this polynomial given you know one of the roots is 6. And you can pause the video and read this mathematical nonsense I wrote up here. But it basically says, look, if a polynomial q is a factor of p, then the roots of q are also roots of p. Remember, that's said all the way over here. This third fact right here, right? The roots of your factor are also roots of your dividend, right? Your starting polynomial. So if 6 is a root of the polynomial, that means it must also be the root of some divisor polynomial. The question is, what is that divisor? Or in other words, since you know one of the roots is 6, what polynomial do you know must be the factor, right? Because the idea here is p of x equals some factor times another factor, right? Some little factor times another. But if the root is 6, then what's this factor? You should know it. And you should be saying x minus 6. So the divisor polynomial, q of x, is x minus 6. Because 6 is the root to x minus, right? That's the root of that. Now, you've identified q of x with a factor, so use either long division or synthetic division to find the quotient. If you like synthetic, we know that this is linear, so we'll just do synthetic. Here's 6, 1, -4, -3, -36, -108. And this is why I really like synthetic, is when you have a lot of coefficients, long division just ain't worth it, you know? This is so much cleaner and faster. 1 times 6 is 6, -4 plus 6 is 2, 2 times 6 is 12, then that's 9. Is that 54? And then 18. And 6 times 18, I'm pretty sure that's 108. So that's 0. So the quotient is, that's the remainder, that's the constant, x squared, x cubed. So the quotient is x cubed plus x squared plus x. Oh, what the heck am I doing? Sorry. I don't. Silly me. X cubed plus 2x squared. I forgot the coefficients. Silly. Plus 9x plus 18. That's the quotient, right? That's the result of the division. Now, part C says you should have found a factorable polynomial. So basically what this is asking is, can you factor this cubic quadrinomial? And you'll notice what I'm doing here is, because it's 4 terms, I'm going to try grouping. So I factor out x squared, I get x plus 2. Then I factor out 9, and I get x plus 2 again, which means this is x plus 2, and x squared plus 9. Yay! So that's the result. That's just the factoring of that. So what that means is p of x, fully factored, is x plus 2. I don't like that parenthesis. It's x plus 2, x squared plus 9. But what was the original thing, right? That thing we divided by was x minus 6, so that's the other factor, because we knew one of the roots was 6. Okay. Now part E says find all roots using that result. So if p of x equals x plus 2 times x squared plus 9 times x minus 6. Well, how do you find the roots? You set each factor equal to 0 every time, right? That's how you find roots. From factored form, you set each factor equal to 0. Now, I should get two roots pretty fast here. That's -2, and this one's 6. For that middle one right there, x squared equals -9. Then to solve for x, you have to take the square root of both sides. And recall, when you take the square root, do plus or minus of -9. We've talked about that before, but as a reminder, when you square a negative or a positive, you get the same. You still get a positive result. So you need to do plus or minus here, right? It's two potential answers. The square root of 9 is 3, but because it's the square root of -9, the square root of -1 we call I. So I have 4 answers here. The roots are this set: -2, 6, positive 3i, and negative 3i. And that is it. You found it. Yippee! Okay, so that's the lesson. That's everything there. It covers just about everything you need to know, okay? Before I let you go and you work on the homework and stuff, notice x squared plus 9 was not factorable. You could not factor that further because it's not a difference of squares. It's a sum of two squares, and there's no identity for that. We got imaginary solutions here. It is possible for one of your factors, let's say it's like this, right? This is not factorable. How do you find the roots? Ask yourself, how do you find roots of a non-factorable quadratic? Quadratic formula. So if you're stuck on one of those homework problems, you might need to use the quadratic formula to find roots, okay? And that is it for this video. Thanks for being here. I hope it was helpful. I hope you enjoyed. And whether it's morning, day, or night, I hope you have a good rest of your morning, day, or night. All right.